intelligence. I think it's not difficult, and I'll start from the very basic things. So I'll start from the linear regression or logistic regression. So the problem is very simple. We wanted to develop some prediction model to uh, to, to predict this nodule, whether this nodule is malignant or benign. So this is starting from very easy things. So we wanted to develop some automatic diagnostic algorithm, which is similar with the diagnostic model. So let's think about easier things. We wanted to predict some person's ages from the number of wrinkles. So we can define this problem as a supervised learning if we have some data, pairs of data with the age and the number of wrinkles. So this problem is, we think this problem will be very easy. So you can imagine that the number of wrinkles are correlated with ages. So we can simply define some model, such as some function, some linear function like this. So this kinds of the problem is the regression problem. It's a prediction of the continuous value, such as age, or some kinds of other variables such as age, weight, or some kinds of prognosis, or any other continuous variable. The prediction of continuous value is we define this problem is regression problem. But for the medical things, we have some different problems. For example, we want to predict. So if we miss some chest X-ray or CT images, then we wanted to develop some prediction model to differentiate the malignant from the benign nodule. This is the classification. So this is the output of the model is the discrete value, such as malignant or benign, or sometimes it's related to some grade, such as tumor grades, or sometimes it's related to the differential diagnosis, more than 2 diagnoses. For example, some diagnosis of the lung adenocarcinoma or lung squamous cell carcinoma or large carcinoma. This classification problem is another problem of the machine learning algorithm. So if we have some data of the CT images combined with this diagnosis, then we can develop some models from this paired data. So we call these kinds of the training algorithm is supervised learning. So the problem can be classified by like this one. If we have some pairs of the known data for data and the label, then from this data we can develop some model. We can develop some prediction model. So this problem we define as supervised learning. But sometimes we have no answer. For example, we have some large set of the CT data, but we don't know the accurate diagnosis. Then we can develop some models to CT images to cluster these kinds of CT images. These clustering algorithms are unsupervised learning. So deep learning or machine learning algorithms can be classified into 2 types: supervised learning and unsupervised learning. Supervised learning is the pairs of data with data and the answer, and unsupervised learning is the problem using only the data. And for supervised learning, we classified this problem with 2 classes: regression and classification. As I mentioned before, the regression is the prediction of the continuous value, and the classification is the problem of the prediction of the discrete value. So the regression or this kind of discrete value prediction is very similar, but we use some different function. Let's start with the simple regression problem. If we want to develop some prediction model of the weight from the height, then we have some training set data such as these things. Then this problem is very simple. So we can define some prediction model like this linear function, a0 plus a1x. So this a1 will be slope and this a0 will be intercept. And the hx is predicted value of the weight, and y, weight, is a real value of the weight. So to develop some accurate model, we should define this A1 and A0 value from this training set. So the problem will be changed. We should define these parameters. We should know these parameters to find the best model to predict the accurate weight. So the basic idea is input A0 and A1 to minimize the sum target. And this sum target is related to some errors. So we wanted to develop some accurate model. So we wanted to minimize the errors between this hx and y weight. So we can define some target. And for this problem, the target can be changed, but in this problem we will deal with this function. This is a mean squared error. So the difference between the hx, the predicted weight, and the real weight, and their scaled value will be mean squared error, and this will be the cost function, and we can define this some target to minimize the objective of the minimized this function. So let's think about this this more simple problem. This is height and this is weight, and simply we can define A0 will be 0. Then we should the considered thing is A1. So to develop the model, we need just only one parameter, A1. So let's think about if we choose any A1 value, then let's think about this value, mean squared error. If we set A1 equal 0.5, then mean squared error will be for this point 0.5, and for this point will be 1, and for this point will be 1.5, and mean squared error will be like this one. Okay, so this is the plot for the A1 and the cost function. So if we choose A1 equal 0.5, then the cost will be this point. And if we choose A1 equal 2, then graph like this, and we can calculate some mean squared error cost function like this one. And the cost function will be minimized if we choose A1 equal 1. So this will be cost value will be 0. So this cost function can help us to find the best parameter from this supervised data. So the hypothesis will be changed. We can define some cost function, and we can generate some model like this one, linear regression, and cost function will be developed like this, mean squared error, and we choose two parameters, A0 and A1, and the target will be minimize the cost. So for this case, we just consider this A1 parameter. However, if we consider two parameters like A0 and A1, this cost function graph will be changed to 3-dimension, like this one. So this cost function graph is 3-dimensional parabolic shapes, and the best parameter will be located in here. So we should find this point. But as you know, we cannot. If we want to find this best parameter, we should input all possible parameters. But for this A0 and A1, there are too many possibilities. So we should find some. We need some algorithms to find these best parameters, A0 and A1. So this method we call gradient descent, and this algorithm is the basic of the deep learning model. So this gradient descent is a very simple idea. It starts from any point of the A0 and A1. So we just input this A0 and A1 as random variables. and iteratively change this A0 and A1 until minimize this cost function. So let's think about this parabolic shapes. First we choose this point, and using this cost function and some differential equations of this cost function, this A0 and A1 value will be changed to like this one. And after the iteration of the training, this point will be moved to this point, and finally it finds the best point. This is the brief concept of the gradient descent. So let's think about more simple problem, like A0 was 0, and A1, just change this A1 value. The function, the cost function will be this point if we choose random variable like 2 on here. And this A1 can be changed after training. For example, hx, A1x. Okay, this is the predicted weight from the height. And we know the real weight in here. So let's think about this point. We have a lot of data from this model. And using this A1 parameter too, then we can generate some outputs of the predicted weight for hx. Then we can calculate some mean squared error as a cost function by the difference between y and hx. So this point will be located here. And then to find the moment of this cost function, we can calculate some partial differential equation like this one. So this cost function is mean squared error, so it's types of the parabolic function. So we can calculate mathematically for the differential equation. This is a slope. So just calculate some parameter alpha and the differential equation from this point. So this slope. So we can calculate the movement of this point. So alpha we call the learning rate. So we can define this learning rate according to our experience for this model, to develop this model. So this alpha, this learning parameter, is important to find the best model, because if we choose very small alpha, then this training process will be the time of the training process will be much longer, because to find this best point, we must move this point a lot of times. But if we choose too large alpha, too large learning rate, then the slope will be changed like this point. So this some kinds of large alpha, then we cannot find some best point here because of the flip-flop situation. So we should choose the appropriate learning rate to find the model. So this is one of the points to find. This is one of the important points to develop some neural network model, even more difficult models. So this is very simple problem. We just have one variable. The first example was the prediction of the weight from the height. However, for many medical problems, we need multiple variables. So we generally call these kinds of problems as a multivariate problem. So, for example, to prediction of the weight, we can use height. However, we can also use some other variables like weight circumference or head circumference, and such kinds of multiple variables. Then we can generate some more accurate models. So this x1 can be height, and x2 can be waist circumference, and x3 can be head circumference, and we can deal with several types of the multiple variables for several medical problems. So in that case, the model is not that difficult, because we already define the cost function, some targets. So even if we have several types of the variables, we can input these variables if we know already pairs of the data, height and weight, so we can calculate some predicted output and here, and already known variable y in here, so we can calculate the cost function by mean squared error. And from this data, we can calculate some partial differential equations for all possible variables of A1, A2, and A3, and repeat these kinds of the running gradient descent algorithms. We can find some the best parameters to predict this weight from the multiple variables. So this is the basic concept of the linear regression using multiple variables, using the gradient descent algorithm. So if we have more than 3 parameters, then the cost function, the function shape will be n-dimensional parabolic shape. So this is a single parameter A1, and we can find some j and a function will be parabolic. And if we have 2 parameters, then the cost function shapes are 3-dimensional parabolic shapes. And if we have more than 3 parameters, then we cannot imagine accurately, but it's the n-dimensional parabolic shapes of the cost function. So there is another problem. This is the problem of the classification. For example, we find some long nodule from the chest PA, chest X-ray, and we wanted to develop some model to differentiate the benign and malignancy. So this is a very simple. Let's think about some simple problem. We have some data of the tumor size from the chest PA, and we already know the final diagnosis if this long nodule are malignant or benign. Then we can draw this plot like this one. If tumor size is less than 3 centimeters, then this nodule are the increased possibility of the benign, and if the long nodule has more than 3 centimeters, then the possibility of this nodule as a malignancy will be increased like this one. And previous linear regression problem is to draw line like this, but we can imagine that we can easily capture that this kinds of the linear regression model is not appropriate, because more appropriate thing will be find such line with 3 centimeters for the classification problem. So to mathematically we can define this model using a logistic function or sigmoid function. This name is same. So this logistic and sigmoid function is defined as like this one, this function, 1 plus exponential minus z, and z is defined by linear regression problem. So this is the combination function using the logistic function with the linear regression problem. And this sigmoid function or logistic function is the function to change from the linear model to probability model. So the output will be the probabilistic score. For example, for 3 centimeters, the probability, the output of the logistic function will be 0.5. So this is the probability. For 1 centimeter, the output will be 1.1 or something like that. And this means the probability of the malignancy is just 10%. This is the probabilistic. This is the logistic function. It is the function of changing the linear function to the probability model. So the output of the logistic function has some value of from 0 to 1. It's ranging from 0 to 1. So this 3 centimeter, we define this point is decision boundary. So decision boundary is just a line for case of the one variable. However, if we have some 2 variables, then the decision boundary is changed to point to the line. For example, let's think about x1 is tumor size and x2 is Hongyoon field. Then this is point x is malignancy and this round is benign. then we can define some boundary function like this one. So this sigmoid function, the lower of the sigmoid function is changing this boundary function as a probability score like this one. So this classification with multiple variables are very similar with the previous problem, regression problem. Previously, the linear regression, the prediction output was the combination function of a1x and hx, or like this. And this logistic classification, just the prediction output is linear function, and finally the sigmoid function is applied to this output c, this hx. So to find the best model, we should optimize this A0 and A1. Previously, for linear regression, the cost function was the mean squared error. But for this case, for the logistic function, what is the optimization function? So let's think about this function, like this one. Log hx, if y equal 1, so if the output is malignancy, and for log h1 minus hx if y is benign. And we can draw the cost function line for y equal 1 like this, and y equal 0 for this one. And then let's combine these two functions like this one. Then we can imagine that the cost function will change to like this one. So it's similar with the parabolic function. So this is the cost function of the logistic classification, and we generally call this function as binary cross entropy. Actually, this the derivation of this cost function is somewhat difficult because we should know about the entropy model of the statistics. However, we don't know such kind of difficult mathematics. So just let's think about this binary cross entropy is the cost function of the logistic classification. So the optimization algorithm is same with the linear regression. So just find some differential equation from this one and select any variables of the A1 and A0, and to find the best parameter using the differential equation from the movement of the parameters. So this is the basic of the deep learning from the linear regression. But this logistic regression can be represented by a perceptron. For example, this is a types of perceptron, and this is same with the multivariable classification or multivariable regression. Let's think about we find some regions, long regions from the chess PA, and we can define some variable features such as region size or circularity or Hounsfield unit, and we can generate some model using these weight variables. This is same with A. And from the activation function defined by sigmoid function, then the output will be the probability of the malignancy. So it's same with the multivariable linear regression model. So to develop the optimize the model of the perceptron is to find the optimization of the W to minimize the error, and the algorithm is the gradient descent. So this perceptron is very similar with neuron. It's because there are several inputs in here, and the output is the single, like the neuron. For the neurons collect some signals from several types of the neurons using the dendrite, and the output will be 1 or 0 for the axon. So perceptron is similar with the neuron. But this single layer perceptron is same as a multi-layer linear regression. However, it has some critical limitation. I think about these types of linear regression will be simply find some decision boundary like in here. However, there are several types of the non-linear classification problem. Let's think about this X is malignancy and this round shape are benign. And let's think about X1 is size and X2 is Hounsfield unit. But these types of the simple classification is not exist in the real world. For many cases, malignancy and benign lesions are mixed like this one. However, we cannot define any decision boundary. However, for nonlinear problem, we can define these kinds of round-shaped boundary. But with the linear regression, we cannot define these kinds of nonlinear boundary lines. So to overcome this limitation, about 30 years ago, many scientists developed another types of the perceptron named multi-layer perceptron. They define some hidden layer like this one. So for this is the input, size, Hounsfield unit, and circularity, and they generate some outputs from these types of the inputs. And from these multiple outputs, the final layer predicts the output, predicts the probability of the malignancy. So they just add another layer from this perceptron. So we generally call these types of this neural network model as a multi-layer perceptron. So mathematically, we can define these models like this one. It's somewhat difficult, but we can easily identify this model using these types of the representation. And this nonlinear classification example is started from very simple problem named XOR XNOR problem. Let's think about this X1 is Y equal A1. So it means this is malignancy. And this is benign. Then we cannot find any linear line to differentiate this X and this round shape. But if we have some types of the nonlinear problem, we can find this decision boundary like round shape. So using just simple perceptron, they cannot find some. They cannot differentiate this X and round shape. However, if we use two kinds of the perceptron, combination of two kinds of problem, then we can solve this XOR or XNOR problem. You can calculate this problem later. So if we use two-layer perceptron, then we can easily solve this XOR or XNOR problem. So this nonlinear classification can be solved by the hidden layer. So this is the linear problem, and this circular boundary decision can be defined by the hidden layer. So this gradient descent can be calculated by this multi-layer perceptron using the backpropagation. This is somewhat difficult problem. However, mathematically we can easily find some differential equation for this output and for this hidden layer and this input. So we can calculate the best parameter for y1 and w1 and w2 by the differential equation according to the computer, not our brain. Anyway, this is mathematically it's not difficult problem for the mathematically. So, however, this conventional neural network has a lot of limitations. For example, let's think about the problem that the image identification problem. We can find some picture like this, but this picture consists of several types of the number, like this one. We see this, however, camera sees like this. So image consists of matrix, but this matrix has very big dimensions. For example, if we find this kind of curved picture, then they consist of more than thousands of the pixels. So the data size is larger than thousands of the pixels. So this problem is the axis of the problem is too large. For example, we just choose 2 pixels, then this is curve, and this is non-curve. However, there are so many pixels in here, so we can add another axis, like pixel 3, and another axis, pixel 4, and so this is the dimension. However, this is the problem of the 7,500 multivariable logistic regression. But it's almost impossible to solve these kinds of multivariable regression because of the curse of dimensionality. We have a lot of data. However, if we have some larger dimension, then the data will be sparse for here. So this is the curse of dimensionality. So more dimensions are more sparse in data space and easy to overfit. This is the core problem of the previous multi-layer perceptron. And mathematically, more dimensions and more weights are mathematically is good to generate the optimized model. However, more dimensions needs more weights, and these more weights are too many parameters to run. So this is difficult to find some best model using the gradient descent algorithm. So previously, around 20 years ago, the better manual features instead of low pixel values were used for the machine learning models. Such as, for example, if we in this era we find some chest PA images, then some model, deep learning model, just find the output like malignancy or benign. However, this is very difficult problem because for the chest PA there are more than 10,000 of pixels. However, previous conventional algorithms uses manual features. For example, for these chest PA images, they extract some manual features like tumor size and tumor Hans field unit and circularity, and such kind of features was the input of the machine learning model. This is the biggest difference between the conventional machine learning algorithm and recent deep learning algorithm. So previously, they used manual features with kernel-based learning, such as support vector machine. And this is one of the common machine learning algorithm in this era also. However, deep learning shows much more, much higher performance than these kinds of kernel-based learning. Anyway, and previously, mathematically, multi-layer perceptron can find some best features, nonlinear features, if they have many hidden layers. However, there is a problem of vanishing gradient. It means, firstly, the error was found in here, such as MSE, mean squared error, and to find the slope for the to find the best parameter for the weight, we should calculate the differential equation of the mean squared error. But firstly, the slope will be large in here. However, according to the backpropagation, the gradient is much lower in the first layer. So this is the problem of vanishing gradient. Actually, this is started from the sigmoid function. For this sigmoid function, looks like this. So for the cases of this here, the slope is almost 0. So according to the backpropagation algorithm, the slope is loose after the many times of the algorithm. So hidden layer, they cannot find some optimized weight according to the previous conventional machine learning algorithms. But to overcome these limitations, deep learning model overcome these kinds of limitations by the new algorithms and recent hardware represented by the general purpose graphic computer machine, GPU, and we collect several big database to run this kind of deep learning model. So deep learning model, I previously mentioned, the most important difference between deep learning model and previous machine learning algorithm is the input of the model. Previously, we select some manual features. However, recently in the deep learning, they use the low pixel data from the imaging, like this one. So previous problem was that there was no good feature from these low pixels, and one of the limitations was the high dimension. And they require many hidden layers, but this make hard to train. But several things are changed. First one is automatic feature extraction using the convolutional neural network. Convolutional neural network is different from the previous neural network. Previously, to calculate the output, they consider all of the pixels. However, convolutional neural network consider just a small area, like this one. So there is three corners in here, and these corners extract the features by striding these corners from the images. This is a more easy example in here. This is the image matrix, and the weight is changed to this filter. Previously, we calculate the weights calculate all of these pixels previously. However, convolutional neural network consider just this small sized area and calculate these filters like in here and calculate this one. This is one kind of the filter, and calculate this convolution here, and this the output will be 2, and for this rate here, and the output will be 6, and applying to this area, then the output will be 12. So this is the mechanism of the convolutional filter, and the purpose of the model is to find some best filter of the convolutional neural network instead of the number of the knobs. So this convolutional neural network is similarly the hierarchical recognition of our vision. For our brain, we firstly identify some line or some textures from the images, like this one, and combining this line and textures, we can identify some kinds of the small portions of the images, head right or some hills, and combining these types of features, we can identify the curves. This is the hierarchical recognition algorithm in our visual system, in the occipital lobe and temporal lobe. And this convolutional neural network has very similar features like this hierarchical recognition in our vision system. So let's think about this image data, and convolutional neural network, the role of the convolutional neural network will find some features like this. They can find some, here is the ear, and here is the eye, and combining these features, they can identify this figure is cat. So this is the convolutional neural network algorithm, and the visualization of the features. They, in the convolutional neural network, firstly identify some line or textures in here, and they find some round shapes or something like that, and they finally they find some image, what is the image. Using this convolutional neural network, they show some quantum jump in the ImageNet challenge, which is an image recognition task. Previously, before the 2012, the image recognition model shows the error rate was more than 20%. However, after the deep learning model, they shows much higher performance than previous machine learning algorithms. So another automatic feature extractor is a recurrent neural network, which is optimized for the sequential data, such as human language or some kinds of the DNA sequencing or music data. So recurrent neural network is somewhat similar with the convolutional neural network, but it's specialized for the sequence data, and this is one of the examples. So this is the kinds of the recurrent neural network for training the Bahu music. So this is training samples, and they randomly choose their music from here. Finally generate some Bach-like music. So this kinds of the example of the recurrent neural network, and this kinds of the recurrent neural network can be combined with the convolutional neural network, and these kinds of neural network are very flexible because this the role of the neural network is the feature extractor, automatic feature extractor. So they can combine these kinds of the neural network, and many things we can imagine. We can generate some models. So previously I mentioned of the Venison gradient. It started from the sigmoid function, but it was very easily solved by some another expansion function. First, previously for the multi-layer perceptron uses a sigmoid function for the hidden layer. For example, we have three inputs in here, and AX1, A2X2, A3X3, and we applied sigmoid function in here to calculate the output of this neural network. Previously used sigmoid function. However, for deep layers, this sigmoid function causes some vanishing gradient. So mathematically, they changed this sigmoid function to another function, rectified linear unit function. This is very simple function. While the output h equals 0 if x less than 0, and hx equal x if x larger than 0. So this is very simple problem, and this rectified linear unit can solve this problem of the vanishing gradient because the slope is 1. For sigmoid function, slope is almost 0 if the x is larger than a specific value or smaller than specific value. So this rectified linear function can solve this vanishing gradient problem. And another problem is the model, the machine learning model is overfeeding. This is a very simple problem. If we develop a model to identify the apple, then this model can accurately identify this picture includes apple. However, some kinds of the models cannot identify this is not apple and this is not apple because they have some loss of the area, and this is yellow, so some model predict this is not apple. So this is a problem of overfeeding, and one of the solutions to reduce this overfeeding is the dropout. This dropout is something like that. For the training, they remove some figures like this, and using these kinds of data, they can train more general types of the apple. So this is a kind of the module of the deep learning. So current concept of deep learning is a multi-layer perceptron, which is started from the linear regression. Very simple model, linear regression, multi-layer linear regression model. And this kind of the deep neural network is combined with the automatic feature extractor, such as convolution or recurrent neural network. And applying to another activation function, such as rectified linear unit, and some kinds of variable modules, such as dropout, are the core algorithms of the deep learning model. So current trends of the deep learning models are high accuracy to various purposes and situations because this model is very flexible. So they use several types of the models to develop much more accurate model, and sometimes they apply to the unsupervised learning model also. So one of the issues is the transfer learning. This is very flexible and scalable model because several types of the deep learning model was developed for the natural images from the ImageNet challenge. It consists of more than 100 or thousands of the natural images, but deep learning models to develop this model can transfer to other problems, such as chest X-ray. So using these kinds of already pre-trained model, this model can be applied to the other images, chest X-ray or CT or MRI, or sometimes for PET or SPECT images. So just train with the smaller data, we can find some very good performance to identify some long nodules or find some differential diagnosis using these kinds of medical images. So this is the brief concept of the deep learning, and we wanted to know how to get the data to train such kind of the deep learning model. And there are several public databases. Some nuclear medicine images are included here, the cancer imaging archives. If we find some Googles right from here, you can find several types of the imaging data, DICOM image data here. It's publicly available. And another brain imaging data can be downloaded from the PPMI, Abide, and ADHD 2000 and ADNI. And for this data, there is no PET data except PPMI. They include thousands of SPECT data. And for other data, there are several PET data, such as amyloid PET and FDG PET, and also paired with MRI. And there are several medical imaging data, such as chest X-ray and mammography, and diabetic retinopathy, fundoscopy images, and some brain tumor data can be downloaded from these kinds of MICAI. And actually, previous deep learning model was developed using very big data, more than 100,000 of the images. But deep learning model requires big data. However, for medical images, it does not requires more than 100,000 or 10,000 of the images, because some types of the tasks for segmentation or super resolution, it just requires 100 or 1,000 of data. And for other types of image generation, such as the generation of PET from the MR images, or generation of MR images from the PET images, they just requires around 100 of the cases. And medical images, we can apply image augmentation by rotation and flipping of the images. And the data size depends on the tasks and complexity of the image data. For example, to develop the model to differentiate Alzheimer's versus normal was trained only by 300 of cases. This is because amyloid PET is relatively simple data because the patterns are not complicated. Just amyloid positive cases and amyloid negative cases, and they are somewhat, the pattern is very linear shapes. So the number of the data to require the number of data for developing the model, it depends on the task and complexity. And to develop the model, I recommend to use Python using downloaded from the Anaconda. You can find some Anaconda Python in the Google. And to learn the Python, the basic things can be learned from the several types of the web application, such as Code Academy. And I already some very simple, very big, basic Python algorithms on the IPython notebook last week. And there are many books related to Python coding in the bookstore. And actually, for the deep learning model, we don't need high-level coding. And to develop some models, we should learn another package named NumPy and Pandas. This is the basic thing of the Python. And if you find some deep learning library, there are several types of deep learning libraries, such as TensorFlow, PyTorch, and Torch, Caffe, and so many types of the deep learning libraries. And I recommend three things. One is TensorFlow, and second is PyTorch, and third one is Keras. And Keras is dependent on it's a high-level wrapper of the TensorFlow. So I recommend the first one is Keras plus TensorFlow. And second, my recommendation is PyTorch. Because these two languages are very simple to use. And next time I will some examples using this one, Keras plus TensorFlow on the Google Collab. And you can find many lectures and resources from the Coursera, which is a web-based freely available lecture. And there are several tutorials in the Keras or TensorFlow website and PyTorch website. And if you have some friends of the computer science or other types of engineering, then you can easily contact them to know this kind of deep learning libraries. So, okay, this is end of today's lecture, and next week we will deal with some real practice using the nuclear medicine data as well as some real image data. Do you have any questions or comments?
For self-learning. For self-learning to encode.
Self-learning?
Self-learning. In your experience, how did you learn? Use book or?
Actually, I actually started this deep learning model around 5 years ago. So I started very low-level languages. Started from the low-level languages. So I did not read some books, but actually this lecture slides. Some of the lecture slides are based on the previous MOOC book. It's Stanford MOOC, Coursera. Some slides include book slides also. Okay, if you have no any questions, then for the next time we'll deal with some the practice in the Google Colab. So actually last week I already uploaded these tutorials, 3 tutorials. So you can learn these things very easily, and according to these lectures and these lecture slides, you can find some meaning like this one. So this first problem is the image recognition task using the handwriting label. Consists of the 10 labels because they are consist of numbers. And next, another topics are Second topic is maybe the deep learning model development for the Parkinson's disease. It's code for this paper, which is one of my paper to apply the deep learning model to find to automatically diagnosis of the Parkinson's disease using the FPCI spec. So we will read this kinds of model next week. And finally, the third topic will be super resolution. Okay, this one. This is the image super resolution, which is the upsampling of the images from the low resolution images. Yes, I think it's not difficult, but maybe the output is here. This is the output of the deep learning model, and this is the real example, and this is the low resolution image. And this model is very easy to train. So next week we will deal with this real practice. Okay, thank you very much.